So good morning, everyone. Welcome back to Math 115. I hope you all had a restful break. I did for the most part, except I was exposed to someone who had COVID, so I'm following CDC protocol and masking. I tested negative as of yesterday, and I'm asymptomatic, so I'm not too worried, but I'm going to follow the protocol, which I guess I looked it up, and it's to mask for 10 days after exposure, so that's what I'm doing. So I'm also not going to come around during group work. That's just for me to feel good about keeping you all safe. So what that means for today, at least, is that we're not really going to do any group work. Probably some of you will rejoice in that, and some of you will despair, but that's just how it's going to be for the next couple days. So I sent you all an email, a long email, with a lot of information. Did you all receive it? Okay. Please do read that email. I'll sort of briefly discuss what was in there, which is, first of all, for homework, you have 5.1, 5.2, and 5.3 are due tomorrow at midnight. And if I'm not mistaken, I posted 5.5 to be due on Thursday, and I'll have a 5.6 homework due Friday. What we're going to talk about in class this week is basically 5.5, 5.6, and 6.1, which 6.1 is right triangle trigonometry. So if you've ever done SOHCAHTOA, we're going back to SOHCAHTOA. So that's what we're going to do this week. Tomorrow there's going to be a group quiz, okay, so really more like a worksheet that I will pass out. You put up to, let's say, like up to 3 people in a group, or do we want 4 people in a group? Okay, we'll do 4 people in a group is the maximum, and if you don't have a partner, don't worry, I'll pair you up with someone. And that will be a group quiz. You'll put all the names on one page. I will grade it as if it was a regular quiz, and all 4 of you will get the same grade. You can also ask me questions during that time, so hopefully I can help you get where you need to go. So that's going to be tomorrow. What else was in that long email? Let's see.
Office hours.
Oh yes, office hours. So. And let me just pull it up so that I have everything there. Yeah, okay, so for office hours this week, we will be reviewing for the exam, basically the final exam. So tomorrow, what I'm going to try to do is have us in cont 109, I think, 109. And we will start reviewing for the final exam tomorrow. Or if you want to ask questions about the homeworks, then you can ask questions about the homeworks or something like that. So that's going to be office hours this week, and I'm going to try to record them and post them to YouTube so that everyone can see them, even if you can't come to my office hours. So that's my goal. And also, class on Thursday will also be a final exam review. So you've got, what is that, like 4 hours of review time with me. And then you'll also have whatever review time you do on your own. You can also send me emails. I recommend that you, look back through as many homeworks as you can, basically, to study for the final exam, because the final exam questions are going to be pulled from all of the homework assignments. I'm not going to have any, let me write this down, no chapter A. Well, no chapter A specific questions. So what do I mean by that? I mean that I'm not going to pull any questions from the chapter A homeworks, so like 8.1 through 8. Whatever. I'm going to start with chapter 1, 2, 3, 4, and 5. That's what's going to be on the exam. Now, you need to know how to do the stuff in chapter A in order to do most of that stuff anyways. So I'm not going to take chapter A specific questions on the exam. The exam is going to be on Tuesday, December 6th at 9 o'clock a.m. So that's our usual Tuesday classroom, which is close hip 201. So note that the time is 9 o'clock and not 8:30. I don't know why, but that's when the exam is going to be. You'll have, I think, 2 hours, and the exam will be like 1.5 times as long as a regular exam. So I'm not going to double the length. I'm going to less than double the length, but you will have twice as much time to work. So you should feel less pressured for time on the final exam. Okay, so while I'm at it, let me also say you can have a 1-page, one-side formula sheet, 8x11 letter size paper, 8x11 letter sized paper, handwritten. Okay, so that should help you. I'll make a recommendation at some point of what I think you should put on your formula sheet, but I won't talk about that now. For now, I'll just tell you that you can have one. Is there anything else I wanted to discuss? Oh, yes, finally, please complete the course evaluation, the course/instructor evaluation. I think there's a separate section for each. So the course section, you evaluate like the content of the course, the structure of the course, the book, things like that. And then the instructor evaluation component, you evaluate me, which is really useful for me because I use it every year to try to improve my teaching. I actually do read those, and I have put many things into practice that I read from the evaluation. So it's really helpful for me. If you could do it for me, I would really appreciate it. So that's the course evaluation and all of the final exam and homework, and this is our last week of class. I'm so sad. I'm going to miss you all. Maybe you're not going to miss pre-calculus, but anyways. Are there any administrative questions before we get to content for today, finally? Any questions about the final exam that are burning inside you? Mm-hmm.
So like in our regular, like how we do in our regular exams, is it gonna be like a bonus question?
Mm-hmm. Yeah, there'll be a bonus question for the final exam as well.
10 points?
10 points? No, it's not going to be 10 points. It'll be like 3 points or maybe 5 points. We'll see. Well, I'll think about it. Anyways, any other questions? Okay, well, you're all very close to the finish line. I know it's hard, but keep up, keep at it, and you're going to finish strong. I know it. So, with that, let's discuss what we talked about last time, and I will actually discuss at length. I don't have a whole lot that I want to do today. What I want to do is just spend a bit of time. Where is this? Jesus. Okay. Here it is. A bit of time reviewing trig equations. So I was thinking, like, I just want to make sure that I cover what is important for calculus most of all. So I skipped 5.4 because I don't think it's important at all. And 6.1 is sort of important, so we'll talk about it at least. But trig equations are quite an important topic, so let me remind you what we talked about last time. So I hope if you didn't come on Tuesday that you watched the recording of the lecture. But if not, here's a refresher for you all. So there's a big difference between what we call an identity and an equation, and I'm glad somebody asked me that question a while back, because now I feel like I know a lot better. So an identity is something that, it's easy to confuse because they both have an equal sign and there's stuff on both sides. But the difference between an identity and an equation is that an identity is always true no matter what x you plug in. And an equation is only true sometimes. Okay? For example, an identity could be something like x plus 2 quantity squared is equal to x squared plus 4x plus 4. This is an identity because if I plug in 1, it's true. If I plug in 2, it's true. If I take any number for x and plug it in, it will always be true. That's why we call it an identity. Okay? Identity coming from the word for identical. Okay? Coming from the word for identical. So these two sides are identical. All right, but an equation, okay, an equation is something which is only true sometimes, okay? For example, x plus 2 quantity squared is equal to 0. We need to plug in a specific x value to make this true. And there are many, many x values which I could plug in which would cause this to not be true. So usually with equations, the game is find the x values that make it true. That's what we did when we studied quadratic equations, cubic equations, logarithmic equations, exponential equations. It's all about getting x and expressing the x values which make the equation true, right? Usually we do that by isolating x, okay? All right, so that's the difference between an identity and an equation. So when we have trigonometric equations, we could have something sort of simple, like sine of t is equal to cosine of t. Now, we know that's not always true, but there will be some times when it is true, okay? And you can visualize these sorts of things in a number of ways. You can talk about the graphs, okay? So here's a graph of cosine is shown in yellow, and a graph of sine is shown in pink, right? So when is sine of t going to be equal to cosine of t? It's when the heights are going to match up for a given x value or t value. So here are two t values, t1 and t2, such that if you plug those angles or t values or inputs, however you want to visualize them, if you plug them into the sine and cosine function, the output is the same. Because remember, the height of the function is given by when you take the t value and plug it into the function, right? You plug it in. You do sine of whatever that number is, and then the height of that is what you will make the height of the pink function to be at that x value or t value input. So if the heights match up, that means that the graphs are going to cross. So, of course, when sine of t is equal to cosine of t, we're talking about the intersections between the graphs of the sine and cosine graphs. Okay, so that's one way to visualize it. Another way to visualize it that we saw was to ask ourselves, well, look, I know that sine of t, okay, if I put the angle t inside the unit circle and I go to the point on the unit circle, sine is going to give me the y value of that point. And if I require a point on the unit circle whose y value is the same as its x value, there are two such points. Okay, one in the first quadrant and one in the third quadrant. So what is my job? To solve this equation, remember, what we are supposed to say, what we're supposed to describe is the collection of t values which would make the equation true. So you can see two angles which would cause this to be true. Here's the first angle, pi over 4. And then also this angle here, which is like 5 pi over 4. Those are two angles which would make the equation true. Are there any other angles which would cause this equation to be true other than those ones? Yeah. There's a whole buttload of coterminal angles to these two angles. How about this one? 9 pi over 4 is going to again point at a point on the unit circle whose y value is the same as its x value. Or how about this one, which would be like, I don't even know at this point. This would be what, like 12 pi over 4. So this would be 13 pi over 4. Okay, so 13 pi over 4 again is going to point there. And then of course I could go around a whole nother time, right? So that would be adding 8 pi over 4. So 13 plus 8 would be what, 21 pi over 4, I think. Okay, so what are we noticing? We're noticing, look, you're going to get a handful of solutions, okay, maybe one or two, which are between like 0 and 2 pi. And then we can add any multiple of 2 pi to either of these angles, okay? So we need a way of describing the collection of all such angles, and there's infinitely many of them, okay? We can't write infinitely many angles down explicitly, okay? So we have to be more clever. We have to say, well, all of the angles which could cause this to be true will be of a certain form, okay? And so to do that, we use set builder notation. Okay, so let's review that. So set builder notation is to say, look, I have x such that, okay, so the way you read this is x, and then this colon means such that, and then you put the restrictions which you're going to impose upon the number x. So you say, look, x is a number such that x is not larger than 2. So this is a collection. It's like a bucket, okay? And what do I put into my bucket? Numbers like 3 go in the bucket because 3 is bigger than 2. Numbers like 1 million are in the bucket, right? So this is a collection of an infinite number of numbers. The only ones that I don't put in are numbers like 0. 0 is not going in because it's not bigger than 2. Okay, so I'm not going to put 0 in the bucket. Okay, so you could express this equivalently by saying, okay, 2 to infinity, something like that. 2 to infinity. But we need to be a little bit more clever than that, because what we're trying to describe is the collection of angles which are coterminal to pi over 4 and 5 pi over 4. Okay, so the way we describe those angles is we're going to say t should be pi over 4 plus 2 pi n. Okay, so n here always represents a whole integer number. So like -2, -1, 0, 1, 2, these sorts of numbers, okay? So n stands for like a nice round, possibly negative whole number. Okay, so we say t is a number such that t is equal to pi over 4 plus any multiple of 2 pi. Or t is equal to 5 pi over 4 plus 2 pi n, where n is any integer. So this is the set, okay? This is like a bucket, okay? And what sorts of numbers am I going to put in? I'm going to put in pi over 4 and 5 pi over 4, right? Just take n equals to 1, or 0, right? And I'm also going to put in numbers like 9 pi over 4, okay? 9 pi over 4. Why is 9 pi over 4 going in? Because 9 pi over 4 is pi over 4 plus 2 pi. Okay? And so this is a bucket in which we're putting in, you know, we're being clever about how we're putting all the numbers in. We can't write them all down, so we describe what they look like. Okay, is that clear? Are there any questions on this set builder notation? Because I remember when I first learned set builder notation, I was really confused. Okay, with set builder notation, there's often a lot of different ways that you could write it, okay? So one way to think about this is to say, look, we take either this angle plus any multiple of 2 pi, or we take this angle plus any multiple of 2 pi. You could view it that way. Another way to view it would just be to say, I'm going to take this angle and add not any multiple of 2 pi, but any multiple of pi. Because I can get all of these ones by all of the angles which point here I can get by taking pi over 4 and adding an odd multiple of pi, right? If I add like pi or 3 pi or 5 pi, I will be, again, pointing down in this direction. If I add a multiple of 2 pi, then I'll get up to here, yes? So you could write this instead as the following. T equals pi over 4 plus n pi, okay? And remember this little symbol here, this funny looking z with an extra dash, that represents the integers, okay? That represents the integers. So don't forget that z is numbers like -2, -1, 0, 1, 2, ... okay? So whole numbers could be negative, could be 0. Any questions on this rewriting of this set? Because these two sets mean the same thing. Okay. It doesn't seem like there are. This is why I spent a lot of time, hopefully, at the start of the semester talking about sets and collections of numbers, because as you can see, it's sort of a recurring theme. So let's see, how much time do we have? Okay. Any questions on this first example here about sine t equals to cosine t? So again, I think it's important to remember that what we're trying to do here is describe, right? If we're supposed to like answer this question, a good thing to ask yourself is like, what should my answer be? Should my answer be a number or a function, or what should it be? In this case, it's a set, okay, which is a collection of numbers, okay? And we're forced to use this sort of set builder notation because we're trying to describe an infinite number of numbers, right? In the past, what we have done when we have to describe an infinite number of numbers, for example, when we're talking about the domain of a function, is an infinite number of numbers many times, we use interval notation. Why can I not use interval notation to solve a problem like sine t equals cosine t? I already know how to use interval notation. Why can't I use it here? Anyone want to take a stab? Yeah, Ashley?
You're looking for very specific values, not all like the values in between.
Yeah, I'm looking for very specific values, and importantly, something which I think you're getting at is, look, they are far apart from one another. Right? They are far apart from one another. If we use an interval, okay, like let's call this T1 and let's call this T2. What is the set T1 comma T2? This is the number T1 and the number T2 and everything in between. Okay? So I can't use an interval like this because the equality is only true at T1 and at T2, but not for any of the numbers which are in between. You can see the height here and the height here are different. The height here and height here are different. Right? So the equality is only true at points which you could describe them as disjoint, okay, meaning they are far apart from one another, okay? and there's no 2 points which are right next to one another, like, there's no 2 points which are right next to one another, i.e. there's no overlap of these two graphs except for at a point. Okay, except for at a point. As opposed to having like an entire segment of the curve which was identical for both. Is that clear? Okay, so that's why we're relegated to using set builder notation. So it takes a while to get used to set builder notation. Make sure you practice it. And yeah. Okay, so let's talk about something more complicated. I'm going to skip over this example because I already did this one last time. But it's instructive. What I want to go back to is something which I was talking about at the end of class last time, which was for number 2 of this problem, and I had to rush through it, so I want to give this a little bit more time. Okay. The way we solved the first one was to basically do the following. We said, well, we divided by 2 on both sides, and then we thought of this as a transformation of the cosine function. So in order to solve this one, I knew how to solve something like, if this is a t and this is 1/2 here, I knew how to solve something like cosine t equals 1/2. So I just solved cosine t equals 1/2, and then I transformed back into x, okay? So that's kind of like a change of variable type of argument. But the second one was a lot more complicated, okay? The second one is a problem that really incorporates, 3 concepts, basically. 3 important concepts. The first concept is identities, trigonometric identities, okay? We use trigonometric identities to replace sine squared by 1 minus cosine squared. That's the first major component of this problem. So let's see how this was worked out. The first thing we did was we replaced sine squared by 1 minus cosine squared. Now, why might I want to do that? Well, I'm trying to solve this trigonometric equation, and I noticed that if I were to replace sine squared by 1 minus cosine squared, then I would get an equation which only has cosines in it. Okay, it only has cosines in it. And that is important for the following reason, which is the second piece of information. The second topic that this problem addresses is equations which are quadratic in form. Okay, so back in the day, we studied equations like x squared plus 2x plus 1 equals 0, yes. But we also studied equations like x to the 4th plus 2x squared plus 1 is equal to 0. And the way we solved these ones was to say, okay, let y be equal to x squared. Then you can rewrite this equation as y squared plus 2y plus 1 equals 0. Then, what did we do? We solve for y. Okay, and once we get y, which in this case would be what, -1? Y equals -1. Then what did we do? We went back to the original equation. We went back to the original equation by reconverting back this. So we know y is equal to -1, which was equal to x squared, and so it turns out that x would be what? Plus minus the square root of -1, i.e., no solution. So let me just go back to this one really quickly, and I will draw the comparison in a second. So I think if you stare at this equation, x to the 4th plus 2x squared plus 1 equals to 0, if you stare at it for long enough, you will see why it can't possibly have a solution. You will see. Because x to the 4th is a positive number. Well, at least it's bigger than or equal to 0. It's non-negative. 2x squared, again, if you take a negative number and square it, positive. So we take a positive number plus a positive number plus 1. There's no way we could ever get 0. we'd have to somehow undo this 1 with like a negative somehow. We'd have to undo the addition of the 1 with a negative. So you can see why this can never be true. But in any case, the way we solve something like this is by converting into a quadratic. Now this equation has solutions for y. Okay, this equation has solutions for y. But it's really important to then go back to x, right? We have to then, so it's kind of like we take the equation, we translate it into another language, we solve it in the other language, and then we try to translate back, but there is no way to translate back, right? So the last step of converting back to x is extremely important because it's possible that the quadratic inform equation has a solution, but our actual equation has no solution. Okay, so why does that work for our problem here? Our problem here says 2 sine squared theta plus square root 3 cosine theta plus 1 equals to 0. So what do? We convert it into cosine. And then this equation is, I claim, quadratic in form if you choose the following translation. X equals to cosine theta. So anytime I see a cosine theta, I'm going to instead write x. And when I see a cosine squared theta, you know what I'm going to write? X squared. So I translate the problem into this kind of an equation. Okay, and this looks kind of scary because it's a quadratic equation, yes, but we have a square root involved. So I'm probably not going to be able to factor this very easily, if at all. So the way that we solve it is using the quadratic formula. Okay, we use the quadratic formula. So we did that, and after we did that, we found that there were 2 solutions. Okay, there was x equals to the square root of 3, and there was x is equal to negative square root 3 over 2. Now it's time to translate back. Okay, it's time to translate back. So how do we translate back? I do believe in you, but I'm going to move this somewhere else. Okay. We translate back by then solving these equations. Remember, we solved the quadratic equation for x, but now we need to move it back, translate back into our original language, which was that x is equal to cosine theta. So I solved the quadratic equation, and I got x equals square root 3 and x equals negative square root 3 over 2. So what I now need to do is go back, and my goal is to find theta such that one of 2 things is true. Either this is true or this is true, because x is equal to one of those 2 things. Cosine of theta is equal to x. But I claim that we actually don't need to worry about this one. Can someone explain why I don't need to worry about this equation? Or why this equation has no solutions, more specifically? I claim this can never be true.
Cosine is never square root of 3.
Yeah, cosine never takes this value as an output, no matter what angle you put in. Why? Because square root of 3 is a number which is bigger than 1. So it's like asking the following. Here, let me draw a unit circle for you, and this will illustrate what I'm talking about. Okay, here's the unit circle, and here's the point 1, 0. So what are we asking for? This is to ask, tell me the angle inside the unit circle which points at a point whose x value is the square root of 3. The unit circle is not that big. There are no points on the unit circle such that the x value is the square root of 3. Because the output of cosine is always between negative 1 and 1. Because the smallest x value that you could possibly have would be negative 1. The largest x value would be 1. Square root 3 is not in the range of the cosine function. So we can't solve, or we can solve very easily, this equation. The solution is that there is no solution. By first solution, I mean solution to the problem is that there is no solution to the equation. Okay? So I claim you don't need to worry about this one for this reason. Okay, so now let's solve the last part. Because, again, what we're supposed to do ultimately is describe the angles theta such that if you plug them in here, here, and here, okay, you get 0, right? That's the goal, is to describe the values of theta, which cause that to be true. I translated it into cosine, and then I translated it into x, and then I translated it back into cosine. In order to say what? This was all to get this relation. But I'm not quite done yet. I'm not quite done yet, because now what I must do still is describe the angles theta which cause this to be true, right? And then if I know that this is true, then I will know that if you plug it in, if you plug that square root of 3 over 2, sorry, negative square root of 3 over 2, if you plug that into this equation here, square it, plug it in here, don't square it, multiply by square root of 3, add 3, you will get 0. So I need to find the angles theta, which cause this to be true. And this is just a problem that we have already done, essentially. Well, we did sine theta equals 1/2, but let's do this one. Okay, it doesn't need to be that big. Okay, so what am I looking for? I want to find the angles theta, right? Such that if I put them in the unit circle, it points at a point, and this point has coordinates. If cosine of theta is equal to negative root 3 over 2, which coordinate do I know? Well, I have the output right here. It's just a question of, is this an x value or a y value? It's an x value, right? Because it's cosine. So I'm looking for an x value of negative square root 3 over 2. Okay, so I shouldn't draw it here, should I? I should draw it on the left side. So let me show you what does negative square root 3 over 2 look like. Maybe it looks something like that. I don't know. Here is x, this is the line, x equals negative square root 3 over 2, right? Vertical lines are defined by their x value. So this is a vertical line. And it looks like about there. The reason that I draw it there is for the following reason. I know that this point's x value is negative square root 3 over 2. I also know the y value, okay, because it's negative square root 3 over 2. You know what number is going to go with negative square root 3 over 2 for the y value, right? What should it be? 1/2. Okay? If you really want to, you can rederive that using x squared plus y squared equals to 1, right? Let y be your unknown and plug in negative square root 3 over 2 for x. You'll be able to solve for y. Okay? So you can use the Pythagorean theorem to solve that if you want. So 1/2 is the height. Square root of 3 over 2 is this length here. What then is this angle? Yeah, this is 30 degrees or pi over 6. Okay, it has to be because it's across from the short leg of a 30, 60, 90 triangle. I know the short leg will be across from the smallest angle inside a 30, 60, 90 triangle, which is 30 degrees. So I know this is 30. So what then is this angle here? 150. Because 150 plus 30 would be 180, which would be all of this. Okay. In other words, it could be 5 pi over 6. So I found the theta which makes this true. It's theta equals 5 pi over 6. And I feel great about myself. That's the answer, right? Who says no? Someone said no. Lakin says no. Why no?
There's another point that also.
Okay, very good. There is another point which also has an x value of negative square root 3 over 2. You can see it down here, right? Let me go with some pink, maybe. Okay, and again, this will be a 30. So what is this whole angle? What's that angle? It's going to be like 210, or if you want, 7 pi over 6. Okay, so fine. Theta is equal to 5 pi over 6, or theta is equal to 7 pi over 6. Okay, now we're definitely done. Or not, right? Okay, why am I not definitely done? I found the 2 points which have an x value of negative square root 3 over 2, and I did all of this work, and I found the angles which point at those points. Aren't I done now? Why not? Why am I not done? There's a whole world of more angles which point at this point here, right? I could do, for example, this angle. This angle would point again at a point whose x value is negative square root 3 over 2. So how do I describe all of the angles which I could possibly have, which would be coterminal to 5 pi over 6? I use set builder notation. Okay, so I do theta such that what? Someone tell me what goes in this blank here. Well, I don't want to use a greater than sign for the same reason that I didn't want to use intervals, right? I didn't want to use intervals because it's only a very select few points, but there are, in fact, infinitely many of them, right? So here, what I need to write is the general form of any angle which is like 5 pi over 6 or is coterminal to 5 pi over 6. I think I heard it. It's 5 pi over 6 plus what? 2 pi n. Yes, I think I heard you say that, Ashley. Okay, 2 pi n, where n is an integer. Okay, so is that my answer? No, I also need to incorporate this. So I could do the following. I could union this set. I'm going to union this set with another set, which is the set theta such that, okay, and I also forgot a theta equals here. What am I doing? Okay, theta equals 5 pi over 6 plus 2 pi n. And then here I write theta such that theta equals 7 pi over 6 plus 2 pi n. N is in z. Okay, so this is my final answer. Okay, what is this object? It is a set. It's a collection of numbers. And what do I put in my bucket? I have a big bucket, and I'm going to put in all of the angles, which are 5 pi over 6 or coterminal to 5 pi over 6. Throw them in the bucket. And I'm also going to throw into my bucket all of the numbers which are 7 pi over 6 plus any multiple of 2 pi. Throw those in the bucket. Now I got a big bucket of angles. Pull any angle out of the bucket. Plug it into this equation. This will be true. Which, if that is true, we deduce that that equation is equivalent to this equation. So the angles which will cause this trigonometric equation to be true are those angles theta, which are like coterminal to 5 pi over 6 or 7 pi over 6. Okay, so this is kind of a badass problem. What do you all think? I mean, it's badass in the sense that it's like, there's a lot of moving parts here, right? I don't know. Like, do you have an opinion on this?
It's a lot. I think we all kind of determined that.
Okay. Well, we'll see some more trigonometric equations next time. Thanks for your attention. If you don't have your exam yet, come get your exam. I don't know if anyone still needs to get it.
So when we make our formula sheet, if we bring it to office hours, can you like look at it?
Sorry, if you could you
When we
repeat
make
that?
our formula sheet for the exam,
Yeah.
if we bring it to office hours, can you like take a look at it?
Yeah, definitely.
Okay. That's all.
Mm-hmm.